So now we can get into it. I will not read the name of all of collaborators. So on the first place, collaborators in SMT solving, but also collaborators in applications. And it is a fun to collaborate in this area. What it is good for, I will try to show you a very simple example about Eve's traveling problem. We are all keen to travel. We are here to exchange and network, and we cannot have enough from it. So also Eve has a lot of travel wishes, say 100. But unfortunately, she is allowed to make only 5 travels. And she has some constraint, like she wants to be physically at A1, which might be IFM 2023. And she has some projects, so she needs to visit one of the collaboration partners at A2 or A3. And she has some restrictions regarding cost and time. On the cost, each travel has a certain cost, which is fixed, and there is an upper bound on the travel budget, and each travel takes a certain number of days, and he wants to travel at least the lower bound of days. This is a typical combinatorial problem, which involves also numbers, so we can encode this problem in a logical formula. The encoding is quite straightforward for this case, so we can take some variables which are Boolean, or 0 or 1 we say pseudo Boolean, which express whether travel I takes place or not. So AI is 0 if it does not take place, then it has no costs and no time duration, or the I's travel takes place and it has a certain cost and time duration. And now we can express the constraint. At most 5 travels, AI need to take place, A1, A2, or A3 need to take place, and there is the upper bound on the sum of the costs for all travels and the lower bound on the time sum up over all travels. This is now a formula of linear real, or if the costs and time are integers, then integer arithmetic. And if we have a solver where we just plug in this formula and it solves up, gives us a solution, or tells us that it is not satisfiable, then we can transform back the answer to answer the original problem. So solving logical formulas is practically relevant. I will show you some integrations of SMT solving into solving such problems. But before doing so, I would like to show you the interest of such an SMT solving at a very intuitive high level to show you which nice ideas are behind, which combine different methods in a symbiotic way such that what comes out is much more powerful than the sum of its ingredients. Then I would like to talk very shortly about our own solver SMT, right? Then I come to the integration and you mentioned some future challenges. Let us start with SMT solving. If we go back to the roots, satisfiability checking is the large area code for checking the satisfiability of quantifier logical formulas. And it goes back, of course, if we talk about automated checking, to the time where computers were invented, and around the 60s, where it were so accessible that in mathematical logic, people started to implement symbolic computations on computers in computer algebra systems. And it included decision procedures for different logics. But then the focus was more on the structural mathematical structures of these problems. And then in the 90s, something has happened, and people recognized how painfully expensive it is if there are bugs in hardware. So also driven by this strong need of industry for verification techniques, sub-solving grace. Sub-solving is a technique for proposition logic, and proposition logic is able to describe properties of discrete systems and in this sense also of circuits. So, for example, bounded model checking is one technique where you can express the existence of bugs. And these are logical formulas about circumstantial propositional logic. And people needed powerful tools that could solve really large formulas in small time. So they were working on it, and in the 90s, a new idea came up to make these tools really very powerful. There is a big community behind subsolving. There is a standard input language, a really huge benchmark library which you can use to test your tools and also to execute competitions, which are there since 2002. There is a forum, satellite forum for exchange and communication. There are dedicated conferences like the sub-conference and journals. And as I told you, I will not go in detail, but I would like just to illustrate this very nice idea from the 90s, which made the system work on really impressively large problems. Now assume we are in logic, right? So assume we have a logic and it has a proof system. I illustrated it with a labyrinth. You can imagine now this labyrinth is my formula and I want to know whether there is a solution. So either I want to find a solution or I want to get the proof that there is no solution. And assume I have a proof system. If my proof system is complete, so my theory is decidable, then basically I know there exists a proof. So if I just brute force apply my proof system, and I start with my axioms, and from them I can derive other things, and from them I can derive other things, then if I follow all possible paths, at some point I will find the proof. Well, theoretically. What about the P equals NP problem? If it is expressible in its decidable logic, we know there is a proof. So, what can be so hard? The problem is that in a certain proof state, there might be infinitely many possible proofs to apply. Or there might be proof derivation that run infinitely long. So there is a proof. I know there is a proof. But I do not know where it is. I do not know where I should start to search for. And even if, for example, for propositional logic, Boolean resolution is a complete proof system, but if I apply brute force, I will do a lot of unnecessary steps, proof steps, because I do not yet know at the point of application whether I will need it for the complete proof. So therefore, Boolean resolution for propositional logic is a way to go, but it is practically not scalable. So the idea was, okay, forget the proof system. We want some heuristics to get hints where are the relevant parts where I need to apply my proof system to get the proof. And the idea was to combine it with exploration. That means I try to, well, stepwise build up assignments, which I hope to be extensible to a solution of the problem. And, well, if I run into conflict, then I will try elsewhere. Of course, exploration itself is also not scalable, right? If you have a Boolean formula with n variables, you have 2 to the n possible assignments. It is also exponential. Forget about it for large problems. So the next idea was, okay, exploration, perhaps we can avoid some unnecessary assignments by applying a lightweight look ahead. Something that is very cheap to apply, and it is impactful in the sense that it avoids to run into parts where I can easily see there is no solution. But this lookout is not complete, because otherwise it would be expensive. So now, when I explore with this lookout, already avoiding unnecessary parts, but still run into a conflict, then I apply my proof system because I know then I'm somewhere what is relevant for this part being unsatisfied. Let me show you on an example how it works for proposition logic. We have three components: exploration, propagation is the name of the look-ahead, and Boolean conflict resolution is the name of the proof system. Assume we have this very simple formula. The two, subsolving and SMT solving are based on conjunctive normal forms, so we will have a conjunction of these junctions of, in this case, literals, being propositions or then negation. So now the system starts always with propagation, because if I would have a clause with just one literal, then I would know this must hold, because A and something, it can only be true if A is true, right? But in this case, we don't have any. So we start with exploring. Which does not work. Okay. So we start with exploring. This we call a decision. Say, now let us try what happens if A is false. And before we try the next guess, we check, can I imply something from this knowledge? And this lightweight look ahead just consists of looking at all clauses, because each of the clauses needs to be true. This needs to be true, and this needs to be true in order to satisfy the conjunction. So I look at each clauses and I check whether all but one literals are already false, because then I know the last one needs to be true. Otherwise, the clause is violated. This is the last chance to satisfy the clause. In this case, it does not apply because we have here A is false, but still two literals are unassigned, and here A is false, but still two literals are unassigned. Okay, so propagation doesn't give us anything. Let us continue and build up our assignment by assigning, for example, false to B. And this can be a heuristic decision, which variable with which value I try. And now I can propagate. So what happens by propagation? If I look at the first clause, A and B are both false, that means C needs to be true, otherwise the first clause is violated. But now if I look at the second clause, then A, B, and B were false, but now assigning C to true makes not C to false, and I have run into conflict. And now we resolve this conflict by applying the proof system and generating a part of a proof. The proof system is resolution. So this clause is the one that is violated. And I look at this clause, because it is violated, not C was the last assigned literal, it is false here, and it was propagated in another clause to be, the negation to be true. And this was this clause. And you see, this is a chain of implication. In one clause, I set a literal to true. In another clause, its negation gets false, might again imply another literal to be true, which is again negated somewhere else getting false, and so we have propagation chains. And Boolean resolution allows us to hang back along these chains and make bridges that express this whole implication chain just in one clause. In this case, we apply to these two clauses Boolean resolution with respect to the proposition C. Boolean resolution tells us if I have two clauses which share a variable in one appearing positively, in one negated, then where this variable will have some value, okay? If it is false, then this clause will be satisfied, but the rest of the other clauses will be satisfied. And if it is true, then this clause will be satisfied by the rest of the other clause needs to be satisfied. So in conclusion, the rest of one of the two clauses, the rest needs to be satisfied. So the resolution gives us either A or B, or A or B, which is adjusting the clause A or B. And it explains what I did wrongly. If I assign A to false, then B needs to be true, otherwise there is no solution. This is a piece of proof, and then I will now backtrack and already at this place, I will use this new clause to imply by propagation that B needs to be true. So by this piece of proof, I get global implication chains at earlier levels. And the process will terminate after a finite number of steps. So this was a revolution. This made SAT solving really so powerful that it got a lot of application domains. And then people ask themselves, if it is so successful there, can we do it also for more expressive logics? First of all, quantify a free first-order logic over different theories. And here I list just some of the SMT solvers. Also, previously I listed some of the SAT solvers out there, but by far without any claiming completeness. I just wanted to show that there are numerous solvers and that the development is continuing till today. New solvers appear, of course, some old solvers are not maintained anymore. And there is also somewhere our SMT red solver, which, where did I put it here? But actually it was started somewhere here because there was no place anymore. So when I started my academic career as a professor, I wanted to do something which was not so crowded. Today we have beautiful areas like AI or computer vision. They attract a lot of people. This is because they are fascinating. But I wanted to do something where there were not so many people around, and at that time there were no SMT solvers for real algebra. That means if you have the reals with addition and multiplication. And I thought, this is a fascinating area, let us do this. Nowadays I know why there were no solvers. But still, this was one of the best decisions of my life. Because this is such a beautiful area and there are so elegant methods that implement things, but fascinatingly, for example, for linear real algebra, we know if you have conjunctions of linear constraints over the reals. We know in theory that the complexity is polynomial in the number of variables. There is only one method that implements this, and this method is the ellipsoid method. It is in practice slower than the exponential simplex method. It is not used. We still wait for the method that will in practice be polynomial for this. And this is an old problem, right? It's still not solved. Even worse, for real algebra, we know if you have no quantifier alternation, then the complexity is simply exponential. Till today, there is no method implementing this. So this shows how complex these problems are. And because we have different interests, I will not bore you with real algebra, but I would like to show you, if my laptop lets me, also the basic idea just of SMT solving, which also got very impressive in its development due to a community behind, that were united enough to agree on a standard input format. That means most solvers get their input in this input language. You formalize your problem once, you can use all the solvers. There is also a large benchmark library which you can take to test your solvers, and there are also competitions. And always there are new benchmarks for the benchmark library to be a bit more diverse. So if you have any problems, please submit to SMT. Okay. I think that Zoom is interacting with my presentation, but I will come back. Okay. basic ideas of SMT solving. Basically, there are three types of methods, and I will show you all three just on an example without telling the details. So let us start with eager SMT solving. The idea of eager SMT solving is to solve first the theory part of the problem by transforming a formula from a theory to proposition logic, and then use SAT solving to solve that. Lazy SMT solving is just the opposite. Solve first the Boolean structure of the problem, and if you manage to do that, then check in the theory whether that is consistent. And the most recent development is MCSAT, Model Constructing Satisfiability Calculus, where the idea is make the work democratic and let the two search go hand in hand in a consistent manner. Let us start with eager SMT solving. So if you have a formula like this is from equality logic. That means the theory allows only some domain, assume it is large enough that we don't get headache from having too few values. And we can only, as a series, constraints add equalities and inequalities between variables. So here I have a conjunction of three constraints. And if you look at it sharply, you can see that it is not satisfiable, right? Firstly, we want to transform now this formula to a satisfiability equivalent proposition logic formula, which we can solve by a SAT solver. And we do so by first encoding the Boolean structure by replacing each equation by a fresh proposition. So for example, let us take E1, E2, E3 for the equations. So I have E1 and E2 and not E3 to encode the Boolean structure. You see that this formula is not yet over approximating. So it has more solutions. If it would be unsatisfiable, it would imply the original formula is unsatisfiable too, but it would not yet mean that if I find a solution for the latter, then there is also a solution for the former. I need to refine this abstraction. And what I need to add in this case is the property that equality is an equivalence relation. That means it is reflective, symmetric, and transitive. And regarding transitivity, what I need to add is that if two of the equations stated to hold, then by transitivity, also x1 needs to equal x3. And the Boolean abstraction of this is if the first and the second equation hold, then the third one needs to hold too. And now this formula is also unsatisfiable. It is a satisfiability equivalent encoding of the first one. Similar approaches can be applied to easier theories, for example, to bit vector arithmetic, which is frequently used for program verification, floating point arithmetic, and some others. But when the theories get more involved, then this transformation is not possible anymore in polynomial time. That means by the transformation, you would basically solve your problem. And then it is better to define dedicated decision procedures for them. And their eager SMT solving is not suitable anymore, but we need something else. For example, lazy SMT solving. I show it to you on an example. Assume we have this formula as input. And again, we first build the Boolean abstraction of it, because I want first to solve the Boolean structure. So again, I introduce for each constraint a fresh proposition, just stating whether this constraint should be true or not. And now I can use a SAT solver to do so. That we already know how it works. So we start with propagating, there is no propagation. Then we start exploring, making a decision. For example, A is false, which you now detect by Boolean constraint propagation. If A is false, then B needs to be true. Otherwise, this clause would be violated. So by propagation, I get B is true. And now in less lazy SMT solving, after each such cycle of a decision and propagation, we consult a theory solver asking, well, A is false, so the first constraint is false. That means X needs to be less or equal to 0. And B is true, so X larger than 2 should also hold. And we ask some theory solvers, let us use it as a black box. And the theory solver will say, well, it is satisfiable, for example, X equals 3. If it is integer or real, it would be a solution. Now the SAT solver continues because we do not have any full assignment yet. Let us try. What happens if C is false? Now by the second clause, it would imply that D needs to be true. And we have now a complete Boolean solution, but in order to know whether the original problem has a solution, we need again to ask the theory solver whether this is consistent in the theory. So we extend the previous constraint set by the concretizations of these two literals. And you see especially that literal D was encoding the constraint X very less than 0. Because we are in the real domain, this constraint itself is unsatisfiable. So now the theory solver will give back it is unsatisfiable, but not only this, we also need an explanation why. In this case, it can be a subset of the input constraints, consisting just of a single one. So this explanation needs to be a theory lemma, a tautology in the theory. And the solver could now say, well, X squared less than 0 cannot be true. This is a general truth. So the SAT solver might build its Boolean abstraction and refine its Boolean statement with the information that D cannot be true. D needs to be false. And then it continues. So this is the idea of lazy or less lazy SMT solving, and it will terminate because there are finitely many Boolean solutions for the abstractions. So at some point, this search will terminate. This is the technique how most SMT solvers work. Now, it works for a lot of different series. If you are interested in which series are there, you can look at the SMT lib page. There is also a graph of the different theories that are implemented in the input languages. And then you will recognize that there is also real algebra as a theory. And I promise you, I will not bother you with mathematical depths for these theories, even though it is very hard for me not to do so. Because it is really, there are so nice things that, because there is a certain mathematical depth behind, it is hard to show this beauty in a short talk. And 1 hour is short in this context. So, but I assume you believe me that it is hard. So in this series solvers, we still struggled. And then there was one idea, this MCZ idea, to improve this situation. And this MCZ was actually designed for real algebra. Well, we have seen how good it worked for SAT solving to combine exploration, propagation, and resolution. And the idea was, let us check, can we do this also in the theory? Does it make sense? So could we make in the theory or just also like Boolean decisions, just explore, guess a value? Check whether this value guess has any implications. And if there is, despite this propagation, we run into conflict, can we generalize it to some observations which are strong enough such that this method terminates? And at the first sight, this idea is crazy because you think about the real numbers. What do you want to explore? There are uncountably many. You can just enumerate them like in propositional logic. And what can propagation mean? But there were some really smart people behind it who came up with the following constellation. Assume now this is part of our formula. X times y squared is less than 0. And we are in the real domain. Now, like before, Boolean search takes place with the same ingredients, but in addition, we will do the same in the theory. So Boolean propagation will not bring us anything. Sorry, it was one too much. But a Boolean decision could make this constraint true. And now we could decide, well, we switch to the theory, and we also want to explore. For example, now we know this constraint should be true, so we could guess a value for x. And theory propagation works the following. We have some guesses of values for theory variables already, currently not yet, but we might have. I know which constraints should be true according to the Boolean search. If I plug in those values, some of these constraints get univariate. So there is only one variable left. And when I want to guess value for this variable, I guess only values which satisfy all those univariate constraints. In this case, I have no univariate constraint in x, so I can guess any value for it. Say 1 is a nice number. Now the theory could continue its search. So we have one more variable, y. Let us check what can we do for y. I guess the value 1 for x. I know this constraint must be true according to the Boolean search. I substitute the value 1, and I get y squared less than 0. We are in the real domain. This is the same constraint as before, unsatisfiable. This constraint itself is unsatisfiable. So now we recognize something was wrong with the guessing of x. And if you have a sharp look at the constraint, you recognize it was wrong because, well, y squared is always non-negative in the reals. So if I want to make x times y squared negative, I must make x negative. And there is a method. It is based on the cylindrical algebraic decomposition, for those who perhaps know real algebra, where it is a decomposition of the state space into a finite number of subsets called cells, where all the polynomials that are involved are sign invariant. And this is the cell that contains our guessed wrong assignment. And it generalizes. So we can generate this automatically. And this is great. And this made the same impact as SAT solving got through the combination of the 3 ingredients. It made the method MCSAT the most competitive one for real algebra. And then, what I'm very proud of, we use this idea with T-propagation decision and conflict resolution to conjunctions of constraints, which leads to different settings. I don't have time to talk about it, but what we derive from the cylindrical algebraic decomposition method is the cylindrical algebraic covering method, which was implemented by my former PhD student in our solver. Then he went to Stanford and implemented it in CVC5, and afterwards CVC5 was the winner of the SMT competition in this category. So you see, this is the nice, there is some ideas, combining methods, we generate other ideas, and each of them have some novelty in it. And this is the beautiful thing. And also this is so nice here that you have different areas, you get impressions, you talk to people, and then go home with a lot of ideas in your head. SMT solving is also such an area. So now, what I did when I started my academic career, I said I wanted to have some news, so we looked at decision procedures for real algebra, which were there in computer algebra systems. And first, we just tried to grab them and plug it into SMT solving as a theory module. And then we recognized that it is not so easy, because SMT solving requires some properties, some functionalities of these methods that have not been there. If you remember, in lazy SMT solving, this set, as long as the theory was consistent, was increasing. You start with one set, then you make more Boolean assignments, you extend this set, you extend this set. And you do not really want to recheck all the time. That means this theory module should work incrementally. It should reuse previous results. And also it needs to give back these explanations, which some methods do not generate in computer algebra systems. So what we did is we started to make these methods SMT compliant, implemented them, and also adapted them to the needs of SMT solving. And some of these adaptations were easy, and some of them were challenging, but at the end, something very nice came out of it. And we implemented in SMT-RAT our ideas. It had, now in the meantime, it is nearly 15 years under development. And we did not start it to be the most competitive one. We wanted it firstly to implement our ideas of decision procedures and also to have it for teaching purposes. So we decided to keep it absolutely modular, which is easy to get into it. If you just implement one module, you do not need to touch the others. But of course, we lose some of the efficiency because you do not efficiently merge things. And when we started the development, we did not find any C++ library for real algebraic computations. There were some, but then they were either buggy or they were not thread safe. So at the end, we implemented our own, which is called CARL. And it implements real algebraic numbers, polynomials as types, but also has some backends to computer algebra systems for some methods that we frequently use, where we cannot compete with long-established libraries like Cocoa, Lib, and some others are also involved. And then we use this to implement solver modules, which can be composed to a solver. Regarding the solver modules, I'm not sure, but I do think this covers all that we have currently. You see that our focus is on algebra. We have a simple modules for SAT solver, which might be also not so efficient. We do not have much pre-processing. So there we lose a lot of efficiency, but I do think that in this one, we have the most variety of algorithms implemented. And here you see the covering that I mentioned, and here also another very nice development just published this year. There is a method of Fourier-Motzkin, the only method used today for quantifier elimination for linear real algebra. And unfortunately, it is doubly exponential in complexity. And using the ideas from the combinatorial search of SMT solving, we built a version which is only singly exponential. But it's still bad, but I mean, singly exponential is much better than doubly exponential. And what I'm very proud of, that this does not only reduce the complexity from doubly to singly exponential, but what is nice when you have a new method and a new proof, it does not only prove something, but it shows the nature of the problem. And this FMPlex method shows very clearly what is the connection between the Fourier-Motzkin method and the simplex method, which seem to be at the beginning completely independent and working completely differently. But when you grab deep enough, then you see they are actually nearly doing the same thing. And this is very nice. Okay, and then we can connect these modules to an SMT solver by defining what we call a strategy. So some module gets the input problem. This will be typically some pre-processing or a CNF converter. Then you can have a SAT solver if you make a traditional lazy SMT solving module. And then each module can have some backends passing on sub-problems. For example, you can invoke an incomplete decision procedure, and if it cannot solve, it can pass on sub-problems to complete one, and so on. You can implement parallelism this way, so several backends can be called in parallel, and you can put conditions under which conditions which backend to call. For example, for linear problems, you want to invoke another backend than for nonlinear ones. Okay, I would like to use the remaining time to show you some applications. And I talk only about some own applications, to be precise, about 5. And I will start with one where I show in a bit more detail how such an integration of SMT solving works. And then I will show you 4 others, just the domain, but without showing you what is happening. But according to the first, you could perhaps imagine what the work, how these things work. And in all cases where SMT solving is integrated as an engine, the structure is more or less the same. You have some software tool that does something, and from time to time, it needs help. There is a sub-problem that needs to be solved. And if this sub-problem can be encoded logically as a formula, then you can invoke one of these tools to check the formula. And if there is a solution, from the solution, you can decode this to the solution of the original problem. So the encoding, you can use the standard language input. And I would like to stress that sometimes the encoding is very important. So you have the freedom to formulate different problems different ways. And if you formulate it one way, it might be more effortful for the solver to solve. If you change some small things, sometimes it is solvable very easily. So it is good to know what is in the solvers, how they work, also the theory solver parts, because then sometimes you can encode it much more efficiently. And I have one of the examples, actually the third one, was where my PhD student nearly gave up. It was from planning, but then we had an idea, and then it turned out very fine. Okay, and once you encode your problem in the standard syntax, you try one, so it doesn't work. You can also try another one because they use the same input language. Okay, so some SMT applications. The first one is the most recent one that we did, and it is from P3net. Perhaps some of you know the discrete version. You have some places, like here, and they might have some tokens, and then you have transitions that connect places, and the connections have certain capacities, so you take away some token from some place and put them onto another place, and this transition fires. Now in hybrid P3net, so actually this example I show is a continuous P3net. We change mine and move from the discrete to the continuous. So now the transitions, you can imagine them as pipes leading a fluid from one place to another. There are sources that just something comes in from nowhere. And here you see the rate. So 4 units of fluid flows through the pipe into this place where the outgoing arrow moves to. There's another place also, and there are also some sync transitions which just move out 4 units of fluid from this place, and they disappear. And now there's a problem, namely, and this problem appears frequently in modeling fluid systems, namely what happens when time passes by. You see 4 units of fluid flows in from here and 4 from here, so 8 units flows in per time unit, but only 4 flows out. But the places have a maximum capacity. Only 8 units can be stored here. So after 2 time units, it will be full. Now what what happens? If you model in different architectures, sometimes you have to model it explicitly. What happens in this case? Is it that it overflows, or is it that perhaps it has no capacity and there can be infinitely many inside? And what is nice by Petri nets is, by continuous Petri nets, is that they have a integrated method, integrated into the semantics, that says, in that case, the rates are adapted according to the physical laws. And then there have been some previous methods which we improved, and now it is really as it happens in physics. After a while, when P1 gets full, well, what happens if a tank is full and something tries to come in? Only as much can come in as flows out, right? So the inflows get reduced by the same percentage. So here we take just the half, which reads now in 2 units per time, and here too. Everything fine, 4 flows in, 4 flows out. Now assume we have another place, which is has an inflow of 1, a capacity of 3, and an outflow now of 2. It starts with a certain amount of fluid in it, but now you see less flows in than out, so now the opposite will happen. After a while, this place gets empty. And also here, an automated rate adoption takes place at this moment, because now only as much can flow out than flows in. So whereas for the full place, the inflows will be reduced, for an empty place, an outflow will be reduced. In this case, to 1. But now, this place, it is full, and according to these reductions, less would flow in than out, then this one was further reduced. So according to physics, if now here less flows in, then this will be relaxed a bit. So there more can flow out. So the restriction of P1 will be relaxed as far as possible. So this is rate adaptation, and this happens frequently in water storage facilities. For example, if you build models of them, you see each time these are the levels of fluid in the tanks, in the places, and you see that it is going up and down. That means that the rates are adapted a lot of times. Otherwise, they would just move linearly all the time if the rate would not be adapted. So the rate adaptation should be efficient, but there are some problems with it. Previous methods assured that the method is terminating, but from the cost that it was depending on the adaptation order, which again led to with different order, different results, and it did not really reflect the physics. Now we adapted this method, but we got the problem that now sometimes the iterative adaptation does not terminate. Like in this case, if this gets empty, it will reduce the outflow. Now, because this is reduced, if this is empty, this will be reduced. And because P2 is full, it will reduce these, especially these two. And now, because this is stronger release than needed by PC, this will relax the reduction, which again will, in a loop, trigger the same adaptation rates. And here you see the rates, the flow rates, depending on the number of adaptations. Let us focus on one of them, for example, on T5, which is here in the middle. And you see that it reduced, then it relaxed, relax. And let us zoom in. Then you see that after a while, it is converging to the right value, but it doesn't reach us. So by iteratively, we converge to the fixed point, but we don't reach it. And then we try to find outways, and then we said, wow, SMT solving. This is the solution. We can just encode the fixed point in a formula and use SMT solving to find a fixed point, and without iterations, we can just set the rates and continue the simulation. We only need to express the factors, this percentage, how much percentage a place of its nominal capacity has, which is always between 0 and 1, then we need to express if there's a restriction on a capacity, who has put this restriction, because only that item can also relax the restrictions. So and this can be either the source or the target of a transition who can put relaxations. And there are some further items. So the relaxing place needs to be either empty or full, and then it needs to be on the right side, and so on. We can formulate how much is the inflow and how much is the outflow of a place by just adding up the reduced flows. And then we just say that, well, if the factor is 1 of a place, it is not restricted, but otherwise it needs to have an owner, and an owner restricts all of its children or parents to the same extent if it owns them. This is more or less, and then we express that it restricts only as strong as possible. So there are some details to consider, but this formula encodes the fixed rate. Solve it, and it is very efficient and works well in simulation. Okay, so the next one I wanted to show you is hybrid systems reachability, which is hybrid systems are systems with mixed discrete continuous behavior, as such as with special challenges on the verification. And in order to verify them, you need some representations of state sets, which are subsets of Rn, so the real space in n dimensions. And for that, there have been different state set representations, so data types to store it and operations on it that we need in the reachability analysis. And then we developed a C++ library, programming library, that implements those representations, such that if you have a new idea how to verify hybrid systems, you can use these representations. You do not need to implement everything from scratch. And on top of it, we also implement reachability analysis methods. We have 2 tools. One of them is Hypro. We already heard in the representation of Rasto for the neural network analysis. And the other one is FlowStar, using Taylor models. And in these state set representations, there are logical constraints that need to be solved, and then we use SMT solvers in the background to solve them. So this is one typical integrated formal methods. In one of the formal methods, we integrate the other formal methods. The other one, this is what I mentioned with planning. So there is a planning competition in simulation, where the task is you have a field where you can play with another or against another team. Each team has 3 robots, and there are machines on which certain dynamically ordered products can be produced. And in order to produce a product, you need to catch up material, bring to some of the machines. Then it takes some time till the machine is done, and some of the robot needs to pick up, bring it to another place. Perhaps you need some additional material such that the machine works, but which you also need to pick up somewhere. And traditional methods work with rule-based solutions. That means human think, in this situation, I think the best is to do this. And these rule-based methods are, because they are complex to formulate already for a single robot, they are not cooperative. So these solutions lose the ability that the robots can collaborate. For example, to pick up something from a machine, you can use the robot that is closest. And then they can agree in the planning who does which planning step for one program. And well, they developed an SMT-based encoding, and it turned out, due to this special idea that I mentioned, that I don't have time to detail, that we got more powerful than these traditional methods, which I'm very proud of, because yeah, it is not trivial to beat something that is out there for a long time. Then the fourth application is testing. So if you have a big system and a complex property, and you want to test it, the problem is to find test cases which are interesting. And then you can use SMT solving as following. You build a simplified version of the system. And in this simplified version, we encode interesting parts. And now we have a certain test domain in which we can take tests. And we want parts of this space where this formula is satisfied. These are the interesting test cases. But getting single satisfying solutions is boring. We want to have all interesting parts. So what we can do is we check whether in this domain phi is satisfiable. If yes, we know there exists at least one interesting test case. But we can also check whether not phi is satisfiable. And if it is true, then there is no interesting test case in it. If both of them are satisfiable, so if the first is, if this is satisfiable but this not, that means there is no test case. If there's a test case but the negation is unsatisfiable, then the whole domain is a test case. And if it is mixed, then we can split it and do the same on the parts. And this way I can divide my test domain into areas which contain only interesting parts, areas which are completely uninteresting, and areas where I don't know there are some interesting test cases but not the whole domain. And this is very helpful because now I can go back to my original system and just consider those parts which are interesting. A similar idea can be used for parameter synthesis for probabilistic systems, which I now don't have details to explain, but it's the same. We get parameter values where certain areas satisfy a certain property, probabilistic property that we want to have. And there are other applications, but it is really very, very wide where you can use SMT solving. Everything where you can formulate a problem over some theories that you can encode logically. SMT solving is a hammer that you can use as a black box. But still there are some challenges. So what I told you are the nice things. It is standard input language. There are some tools you can use even online, so you do not need to install it. There are programming interfaces, so you can also use it directly from programs. Most of the solvers have C++ and Python interface. And you can use it as a black box, even though it is good to know what is inside to use them efficiently. And, well, I'm already a bit over time, but what is a new area is certification. So if there is no solution, if there is a solution, then we can just plug it in. Well, it is not always so easy, but theoretically, it is easier to check solutions, whether they are really solutions. But if there is no solution, then if your system has a bug, then basically it's a wrong answer. So it is good to generate a certificate that you can recheck in a peer-reviewed bug. And there are some other issues where interesting developments take place, like optimization. Some theories are supported, some not. Machine learning to have heuristics, quantify formulas, quantify elimination. All those are research areas where research is going on. So as I said, if you want to submit a paper to those conferences when you do not know what to do, there are a lot of open problems. Yeah, thank you for listening, and I'm happy to answer questions.